Alright, the other effect that happens when we talk about transferring chemicals between two tubes is as follows. If we say transfer chemicals from tube 10 to 15, it says take these chemicals and these chemicals, connect them through a conduit, let things flow. That's fine when we have these discrete, really wide tubes, but as these tubes get thinner and thinner, here's the setup. We might have a tube at 10.14 and another tube at 15.63. And if the source and destination are exactly 10.14 and 15.63, it says transfer some chemicals between this tube and this tube. But this tube right next to it at 15.64 is not involved in that operation. And it's cleaving space into these really tiny little subsections and acting as if what happens in this subsection is totally independent of what happens in the section next to it. And that makes less and less sense as we shrink delta x to 0, which is our goal here, is to make this thing continuous. So instead of having this discrete transfer from one point to another, we spread the effect out. So for example, this tube 1 says, let's transfer between 10 and 15. But when we specify that, we also say, let's transfer between 11 and 16 and 12 and 17, as well as 9 and 14 and 8 and 13, and so on. So one transfer actually specifies a transfer between a lot of different locations in the system, but the most intense transfer is going to be between 10 and 15. So those get connected with a very thick conduit. And the connection between 10 and 14, that's not quite as thick. And the connection between the next tubes will be even thinner. So we're changing basically the diameter of this connecting tube between pairs of chemical containers. And this instruction specifies the center point for that set of transfers. But in fact, we have transfers going off infinite distances in both directions, all the way down to, in this case, 0 or 40, but if the system extends forever, all the way off to forever. So imagine, if you will, something like an e to the minus x squared curve. That peaks out right at 0 and then fades off in both directions. We call this the effect. And the effect is basically scaling the transfer rate, or if you like, it's the tube diameter of the connecting tube between the bins specified by some instruction. So if we have a 10-15 instruction here, this says we're going to have a tube of diameter 1 connecting tubes 10 and 15. But over here at a distance of 1, which would be tubes 11-16 and tubes 9-14, we might have a tube of diameter 0.7. And over here at a distance 2, we might have a tube of diameter 0.2, and so on. So the further out we go from the center point, 10-15 in this case, the smaller the connecting tube and the less chemical transfer we have. The dominant effect is between 10 and 15, but there's still an effect nearby, and in fact it goes on forever until you hit the end of your space. So this is called the effect, and we can control the thickness of this curve, and that corresponds to how much this effect applies. Now if we shrink this curve all the way down, it becomes something like an impulse function, which is 1 here and 0 everywhere else. That's the previous case, where 10-15 says transfer from 10 to 15, don't transfer anywhere else. If we spread it out in the other dimension and just make it 1 everywhere, then anytime we say transfer 10-15, we also say transfer with the same flow rate from 11 to 16, 12 to 17, and so on. So we can play around with the shape of this and see sort of how localized these instructions are versus how distributed they are. So that's the other component of this, is having a distributed effect. So this gives us a system with simultaneous execution, continuous time, continuous space, and a distributed effect. And that's basically the central ideas of the EEXIST system.